roughly the identical size as Earth, its function inside the livable zone indicates it is able to certainly have conditions appropriate for life. Proxima B's proximity also makes it a super target for our quest for existence beyond Earth. With it being so near, it's a high candidate for interstellar missions. Reflect on exploring this Earth-like exoplanet. Despite the fact that we cannot yet move there, it's certainly on the radar for future missions. As technology advances, it is one of the most thrilling endeavors within the field of space exploration. But it's no easy undertaking. It would take 75,000 years for spacecraft like Voyager 2 to reach the Proxima Centauri system. Nonetheless, a solution has been proposed. Solar sails. These extremely thin sails can be used to propel a spacecraft to the Alpha Centauri system and Proxima along with it. This technology uses solar pressure to keep the spacecraft on course, eliminating the problem of running out of fuel. And here's something even cooler. This cutting-edge technology could offer insights into the possibility of life on other planets like Proxima. However, like anything ambitious, there are barriers. For example, the presence of an atmosphere does not necessarily guarantee the presence of life. Proxima b could be like Venus, with a thick, hot atmosphere that is inhospitable. Furthermore, get this. The James Webb Telescope can locate such emissions if it reaches a brightness of only 5% of the sunlight hour side. Now, 5% may not look like much, but when dealing with a star that is normally dimmer than our own sun, it's quite significant. If Proxima b has advanced civilizations, they'll use bright orbital mirrors to reflect sunlight from the daylight side to the nighttime side. How cool is that? There are infinite exoplanets waiting to be discovered in our universe. These planets come in all sizes and shapes, with some being big gas giants, while others resemble our very own Earth. But what can we understand about them? One type of exoplanet that has caught the attention of space scientists is the gas giant. These planets are comparable in composition to Jupiter and Saturn, but are much larger. A number of these behemoths have been named super Jupiters, surpassing even the biggest planet in our solar system. Yet it's not all. There are also hot Jupiters, gas giants that orbit extremely close to their host star, existing in a sizzling world with temperatures that would melt steel. Imagine seeing one of these planets up close, with its furious storms and extreme heat. In addition to gas giants, there are also Neptunian exoplanets, which are similar in size to Uranus and Neptune. Among these are the hot Neptunes and small Neptunes, which are smaller and closer to their host stars than their gas giant cousins. These planets are often shrouded in mystery, with their atmospheres being tough to study from a distance. And let's not forget the Earth-like exoplanets, which resemble our own Earth. These planets come in various sizes, ranging from smaller than our planet to twice its size. There are even super-Earths, which have masses more than twice that of our planet but are lighter than Neptune. One of the most fascinating exoplanets recently discovered is Proxima Centauri b, which orbits the famous star of the same name. This planet is classified as a super-Earth, with an estimated mass of 7 Earth masses. It orbits in the habitable zone of its host star, and scientists are currently investigating whether it could support life. Proxima Centauri b is of particular interest because it is the nearest potentially habitable planet to our own solar system. As we continue to explore these captivating worlds, the James Webb Telescope promises to offer even more insight into their potential for life and habitability. The allure of Proxima Centauri b lies not only in its proximity, but also in the tantalizing possibility that it could harbor conditions conducive to life. As we probe deeper into the exoplanet's characteristics, the question on every scientist's mind is whether Proxima holds the keys to understanding whether life can exist beyond Earth. While it may be a rocky world, its orbital position in the habitable zone and its potential water presence make it an exciting target for future exploration. However, there may be a catch. The proximity of Proxima Centauri b to its star means that it could be subject to risky radiation, especially since red dwarf stars like Proxima Centauri are known for their violent flares. These flares, which emit extreme bursts of radiation, could strip away a planet's atmosphere over time, making it difficult for life to take root. Proxima may also face tidal locking, a condition in which one side of the planet is always facing the star while the other side remains in darkness. This could lead to high temperature variations between the two sides, complicating the conditions needed to support life. But there are still many uncertainties. We do not fully understand how the planet's atmosphere interacts with its surroundings. For example, could Proxima b have a protective magnetic field that would shield it from the star's radiation? This could be crucial for sustaining life on the planet. Furthermore, the possibility that life, if it exists on Proxima b, could have adapted to the harsh environment cannot be ruled out. Life on Earth, after all, has managed to thrive in even the most extreme conditions. From the depths of the sea to the frozen tundra. Could Proxima b harbor a different form of life, one that thrives in the face of challenges we cannot even yet imagine? In addition to these considerations, Proxima b's proximity to Earth makes it a prime candidate for interstellar travel, especially with future advancements in space technology. While our current spacecraft like Voyager 2 might take tens of thousands of years to reach the system, more ambitious initiatives are being proposed. Solar sail technology, for example, offers a potential solution. Using the pressure exerted by sunlight, solar sails could propel spacecraft at a large fraction of the speed of light. This method could bring us closer to realizing the dream of sending probes to explore remote exoplanets like Proxima Centauri b. The possibility of someday sending people to Proxima b is an even more tantalizing opportunity. While this prospect remains far off, it fuels our imagination and underscores the importance of continued exploration and research. For now, the James Webb Space Telescope will serve as our eyes into this distant world. It will monitor Proxima's atmosphere, study its surface, and gather critical data to help us determine whether it can support life. Through its infrared capabilities, Webb can provide us with valuable insight into the planet's weather patterns, composition, and more, bringing us closer to understanding whether Proxima b could eventually be a second home for humanity. As we move forward, it is clear that exploring exoplanets like Proxima b offers more than just the chance to find alien life. It also represents our desire to understand the universe and our place within it. Every discovery, every piece of the puzzle, brings us one step closer to answering fundamental questions about life, the cosmos, and what the future holds for humanity. Whether Proxima b proves to be habitable or not, the journey of exploration will continue to inspire and shape our future. Suggests that the universe does not recognize our idea of vacancy. The fields and forces continue to fill the universe with a hidden energy that prevents absolute nothingness. This understanding raises an exciting question. If fields make particles and particles make matter, should the universe itself have emerged from this nothingness filled with quantum fields? Dark energy is a mysterious force that currently drives the increased expansion of the universe. But did dark power exist earlier than the huge bang? From certain perspectives, the truth that dark energy exists nowadays is a leftover of an electricity subject from earlier than our universe's development. The properties of dark strength seem to indicate a giant hidden force that could have existed in some form prior to the Big Bang. Some theories advocate that dark strength in a far more potent nation may have controlled the inflationary stage, causing rapid growth. The presence of dark electricity suggests that, no matter whether or not our universe had been exhausted of all count number and radiation, this pressure might continue to amplify the fabric of spacetime. This notion ends in a frightening question. If dark energy became present before the Big Bang, could it have formed the instances that led to the beginning of our universe? Could dark energy be the silent architect of inflation, or even the actual starting of our universe? As we explore this opportunity, we face the ability of dark energy, not just as a pressure shaping our universe, but as a key that could unlock the secrets and techniques of the multiverse itself. Another principle that gives an alternative to the Big Bang as the last beginning is cyclic cosmology. The idea that the universe is going through countless cycles of beginning, dying, and resurrection. On this model, the massive bang is not a one-time event but rather a part of an undying rhythm in which universes extend, crumble, and then regenerate in another cycle. This idea indicates that our universe could have been reborn from the remnants of a past universe. The manner of contraction and growth in a cyclic pattern might mean that there was never a real beginning, but alternatively an eternal series of universes emerging, developing, and renewing themselves again and again. Cyclic cosmology raises large questions about time, because it shows that time itself might be cyclical instead of linear. If this idea is correct, it could suggest that what exists before the huge bang was just another model of the universe, one which collapsed only to give birth to our modern-day universe. For researchers, this concept gives a wealthy answer to the question of closing origins, featuring that there's no real beginning. The universe has always existed in some form, transcending our thoughts of time and life. Early-stage gravitational waves are another exciting concept that might hold clues to what existed earlier than the Large Bang. Gravitational waves are ripples in spacetime due to big cosmic occasions, and scientists trust early-stage waves, if ever detected, ought to monitor insights into the universe's earliest moments. Those waves ought to serve as the echoes of what came before the Big Bang. Should they be recognized, they may offer proof of the universe's preceding states. The ability discovery of early-stage gravitational waves is one of the most interesting possibilities in cosmology today, as it may not just monitor the truth about the massive bang, but also provide a glimpse into the cosmic state before, or even before our universe was born. This theory gives a tantalizing prospect, detecting gravitational waves that might act as fingerprints of a pre-Big Bang universe. As we continue to explore what could have existed before the massive bang, we delve into concepts that push the boundaries of our understanding, challenging even our most essential assumptions about space, time, and life itself. One of the most mind-boggling ideas comes from the field of quantum gravity, a subject that seeks to merge quantum mechanics with standard relativity. This merger could probably monitor a unified idea of everything, and may provide perception into what existed before the Large Bang. Quantum gravity suggests that space and time are not simple continuous entities as we experience them, but rather are discrete granular structures. This concept posits that the fabric of spacetime itself could have been formed from a microscopic Planck scale shape, with tiny quantum fluctuations shaping the universe in ways we can't yet absolutely recognize. In this view, what we understand as the smooth continuum of space and time might have only emerged from those fluctuating quantum fields. As a result, before the Big Bang may be defined by a significantly more extraordinary concept of reality, one wherein space and time themselves were not absolutely formed. Another possibility is that the universe is part of a giant cosmic panorama of viable universes, each with distinct physical laws and constants. This principle, known as the string panorama, arises from string theory, which suggests that all essential debris are virtually tiny vibrating strings. In this framework, there are numerous possible configurations of these strings, each similar to a special set of physical laws. The string panorama should mean that our universe is simply one among many, each arising from its very own awesome Big Bang-like event. The existence of such a panorama also brings forth the perception that different universes might have unique dimensions, different strengths of gravity, or maybe exceptional types of count. In this view, our universe might not be unique, but rather part of a multiverse, a group of universes, each evolving independently. The multiverse theory offers a speculative yet fascinating solution to the question of what came before the Big Bang, another universe in a different configuration, probably leading to infinite cycles of introduction and destruction, with no definitive origin. In addition to those cosmological fashions, a few theoretical physicists have also considered the role of black holes in shaping the nature of the universe. A hypothesis gaining attention is that our universe may be the result of a black hole formed in another universe. In this scenario, the singularity at the middle of a black hole could function a gateway to another universe, with a Big Bang being the moment when such a black hole gave birth to our cosmos. This hypothesis is supported by the truth that, according to general relativity, the singularity at the center of a black hole is a point in which space and time curve infinitely, creating a region where the recognized laws of physics break down. It's possible that the extreme conditions inside black holes could cause the advent of new universes, which might also suggest that what we recall the Big Bang was just the beginning of our universe from the singularity of an historic black hole. Exploring these concepts requires a deep dive into the very nature of time itself. Some cosmologists speculate that time, as we apprehend it, may have had no meaning before the Big Bang. If time started with the Big Bang, then there may also have been no before in any traditional sense. According to this view, time itself may have emerged from a quantum fluctuation or from a primordial kingdom in which the usual differences between past, present, and future did not apply. This may lead us to rethink the idea of causality, which is predicated on the idea that events happen in a linear sequence. If time did not exist in the manner we experience it, then the question of what came before the Big Bang becomes nonsensical, as there could be no temporal framework to support it. Further complicating the picture are theories of cyclic time, as discussed previously. Cyclic cosmology indicates that the universe undergoes infinite cycles of start, evolution, and eventual disintegration. On this model, the Big Bang could constitute just the most recent jump in an eternal series of universe cycles. These cycles might not be equal, but could evolve in distinct directions, each with particular physical properties. The cycle of the universe, according to this principle, could be a continual process without a real beginning or end, rendering the question of before the Big Bang meaningless in the conventional sense. The concept that time itself is probably cyclical suggests that each Big Bang may be accompanied by a contraction and another big crunch, with a universe reinitiating itself in an endless loop. Another avenue of investigation into the nature of the cosmos is the potential of a primordial soup of particles and fields that existed before the formation of stars and galaxies. This concept suggests that, before the universe started its rapid expansion, it was packed with a dense and hot aggregate of essential particles, including quarks, leptons, and bosons, all in a state of excessive energy. These particles could have been interacting at very high temperatures and densities, laying the foundation for the formation of matter and energy. As the universe cooled, some variations of this theory propose that this primordial soup existed in a quantum foam, where particles continuously emerged and vanished due to the uncertainty principle of quantum mechanics. The properties of the soup could potentially provide insights into the universe's earliest moments, and by extension, what preceded the Big Bang itself. In the end, what existed before the Big Bang remains one of the most profound mysteries in science. As our understanding of quantum mechanics, cosmology, and essential physics deepens, new theories will continue to emerge, offering more and more complicated and sometimes paradoxical views for the origins of our universe. Even as we may never fully grasp what came before the Big Bang, the pursuit of this knowledge will continue to stretch the boundaries of human curiosity, driving us to explore the unknown frontiers of life.